A professor of mine fondly calls a group of people as crackpot physicists. I call them with a more respectable term of fringe physicist. And I recently saw a video of a fringe physicist talking about why special relativity is wrong, and he had a good question. And this is why I go to watch fringe physics videos from time to time, because sometimes they ask you good questions that you should be able to answer as a physicist. Sometimes they ask questions that are really open. Sometimes they ask questions that seem like obvious. This is an obvious flaw in modern physics or current physics. But then if you think a little bit about it, then you realize, oh no, this is not he. But they make you think. And this is one of those questions that I would also pose to you, and you could think about it and see whether you can answer it. The question goes like this. You know from experience that if you are in a car which is going at 100 kilometers per hour with respect to the road, you throw a ball at 10 kilometers per hour with respect to the car, with respect to yourself, then with someone on the road would see the ball move faster than 10, something like 110 kilometers per hour. So the speed of the car gets added to the speed of the ball. This is known. But when you start learning about special relativity, the first thing that they tell you in many textbooks that this does not happen with light. So if you have a laser pointer, and if you are on the road and you point the laser pointer, and someone on top of the car, sitting on top of the car, points the laser pointer at the same place together, they press the buttons, you would still see the front of the light does travel at a finite speed, so the laser must be traveling like this, but it would travel together. So basically the speed of light is not enhanced by the car. The speed of the car does not get added to the speed of light, and this is something that we start relativity with. I'm going to write this here because later I am going to explain to you that this is not special. This is not special about light. Speed of medium. Uh, Forget what. Forget that about that for now. And now, of course, when you accept that speed of the car does not get added to speed of light, how do you explain this? That this is another another way that textbooks, especially popular science textbooks, explain relativity. Imagine that you are on a platform, and there is a train carriage uh, that you see, and then there is a laser pointer at the bottom of the carriage, and the laser shoots upwards, and since you are on the platform, this red is the platform, the view seen by platform, and the blue is the view as seen from the train carriage. Now if you are inside the carriage, you see that the laser travels in a straight line and touches the roof of the car. And if you had a laser, if you have a laser, you can try this. You point it upwards, it just points exactly on top. Okay, but from the car, the same laser would travel, the laser beam would travel like this, because the whole carriage moves uh, from here to here. So if I could to mark, I could draw these start and end points, and here I would draw them in blue. And the the carriage was here initially, and then it moved how much distance? It moved, right? So as you see, this point is still at the midpoint of the carriage. So you see that the laser beam traveled like this, and this is where the gentleman had a problem, where he said that you said that the speed of the car does not get added to the speed of the light beam, but then you are adding it. You are adding it. And we threw the ball linearly, but you could also throw the ball upwards when you're sitting on top of the car and it lands back in your hand. If there is wind, of course the wind will blow it, so do it inside a railway, in a train carriage or in a bus, which is going very smoothly. So ideally you would have to be in a nice maglev train, and when you toss the ball it lands in your hand. So for you the ball did this, but for someone outside the ball did a very long parabolic motion like this. So the moment you launch the ball, for you it has this velocity and this only, but for someone outside the ball has this velocity that you gave, let us say 10, and then it has this velocity that the train already has, like 100. So it has this total velocity. Well, in this case, because it's 10 and 100, it would be more like this. So the speed of the train got added to the speed of the ball, and that's why the angle was different. And so in that case this is something similar happening to the train. Let me do this so that you know that it's in motion. It's a little bit confusing to draw it at different times. So the question is, then aren't we contradicting the first thing that we set out with? Although this is not an assumption in relativity, this is more basic and we'll come to it later, but aren't we contradicting this? Okay, I have the written speed of the medium and I'm pointing it to it as though you'd understand, because medium you must have started being confused with when I said medium. Speed of a wave, uh, just anyway. So now what is your answer? If you have been, you're a physics student and you have studied relativity, what is your answer? You could, if you want to think about it, close the video, come back to it later, because I'm going to reveal it to you now. Now let us, if the person had this fringe physicist had thought a little bit about it, he might have understood it, because this goes into heart of relativity, that if you say, that the person on the platform should also see this, why should he see that, why at all should he see this, and he should see the light moving absolutely and the train moves away and light goes upward? Why should he not see this? Now of course it would contradict with the fact that the person in the train thinks that the light hit the spot on top, while the person on the platform thinks that it hit the spot slightly behind, and they have to agree because either the light hit the spot or it didn't hit the spot. So they cannot disagree on something like that. But you might say that, don't, the speed of the train 100 kilometers per hour is nothing compared to speed of light, which is 300,000 kilometers per second. So it's tremendously large, and perhaps they cannot detect it, and perhaps we don't have instrumentation to detect something like that yet. So let us imagine that this distance is very small, and that's why they do not agree. But even if you say that it should have, for both of them it should take the same path, then you are really saying that there is a universal frame in which such a path exists, and everywhere else every other observer would agree that a laser launched from a point here goes like this. Then every observer in the world would also agree that this point and this point do not move, they are always like this. But we do not have such a system of reference, and of course it does not contradict relativity. This is relativity, that when I have a laser pointer and I point it towards the roof, then it lands on the roof. If it had landed somewhere else, right, then I would have known, okay, I'm letting the laser go and it's going linearly like this, and it's touching over there. That means that my velocity is exactly, well, you could say I know the distance between the roof and the laser, I know how long it took to reach, so I can calculate uh, how much my velocity absolutely is with respect to that frame that doesn't move. But we do not have such a frame, and we have tried and tried and tried, and we cannot find a frame like that with in which light travels, uh, I mean, this is not even special relativity. This is Galilean relativity that we're discussing here, because special relativity is not about absolute space. It's about absence of a measure of absolute velocity. Absolute space we don't have, and we have known about it for a longer time than special relativity. Now let me come to this. Hopefully you understood this, because even if you wanted to say that with respect to the train, the laser went like, should have gone like this and train should have moved, the fact that the platform is moving itself, with respect to the stars and with respect to other galaxies, it's moving at incredibly high speeds. Why should it be like this at all? It should be some random um, trajectory, but we do not see it. We do not see it at all. And this is the core of relativity, because it's saying that regardless of which room, which car, which train carriage you are in, if you point your light laser upwards, it will behave like anywhere else. So you can say that you are not moving at all. You are allowed to say that I am allowed to say that this room is not moving, and everything else that I see moving, for example, I might see an asteroid move away. I mean, I look at stars and they have proper motion, so the stars, I see them moving and I think that the stars are moving and I'm not moving. I'm allowed to say that. And physics works exactly the same. And that's what special relativity is, that even light behaves, um acts as though we are not moving at all. Now let me come to this part that I promised that I tell you. Why is it's not part of special relativity at all? Because it happens in sound also. So if you are on a, that's a weird train. I mean, who has seen this steam train these days? I mean, I'm trying to remember what the Hogwarts train looked like. Okay, anyway, and then you shout from top of the train, and this is of course audio sound wave. Then you shout from the top of the train, the sound wave would only move at the speed of sound in air. It would not, the train speed of the train would not get added to the sound wave, which is actually comparable in this case. And what you would rather instead see is Doppler effect. And I'll make another, like right after this I'll make a video about Doppler effect. Another good question that I had myself is that maybe the speed is getting added, and what you see as Doppler shift really is a wave coming faster than it should. But for this video, what you need to understand, that it's a property of waves in a medium. It's not a property of it's not a property of light. Specially, it's not a special relativity thing. It happens to sound also. What is different with light and sound is that with sound you can detect the wind, if there is wind blowing. So now imagine that you have another friend here, and so as we said, if let us say that you are here and you have two friends who are doing this experiment, and with respect to you don't feel any wind at all, and let us say that if he were not on the train, there is a fourth friend here. They both shout at the same time, and if there is some distance d and the speed of sound is, I don't know, let us call it whoa, it doesn't matter. So the time taken would be the distance divided by whoa, or weight. It doesn't matter if you can't read this. So no, okay, I don't want to confuse you, so let me just call it vs, speed of sound. Okay, and it would be the same even if he's on the train, this friend, and he shouts, the speed of the train does not get added to speed of sound, and both of the sound waves come at the same time to this friend, except that the sound emitted by him would be higher pitched. So um, that's the only difference he would notice, but he would not think detect this one faster earlier. And now there is a question of wind. You are here, what you can see, if now wind is blowing, if wind starts blowing in this direction, then you would see that he detects both of them at the same time, but earlier than he would if the wind was not blowing, or especially if the wind was blowing in the other direction, because it would slow down the sound. So and if the wind was blowing in the backward direction exactly at the speed of sound, which I don't know if it's physically possible, then the sound wave would just remain in midair like this. I mean, technically it is traveling because it doesn't know that the wind is moving. It's just doing this and it thinks that it traveled. I mean, in the volume of air that moved, it did travel from one atom to another atom. Um, but for a person on the ground, it would look like it's standing still. So it's a property of waves itself. This was a bonus part which probably went longer than the original video. In the el video siguiente, the next video, we will talk about, I'll answer to you my answer. And this is a question that I had, that has anyone tried coming up with a theory where the blue shift that you see, it is not because when the blue shift is because the speed is indeed getting added, but if you expect the wave to come at the same speed, and if it comes faster, you would interpret it as blue shift, or being higher pitched Doppler shift. So you would rather instead choose to think that it's Doppler shifted, instead of thinking that it's a wave at a faster speed. So it would be an assumption that the speed is not added to the wave, and maybe this is a conventional choice and not a real fact, and maybe the reality is open to considering whether the speed of the emitter gets added to the speed of the wave or not. And in the next video we'll see why that. Oh, could you hear me properly? It was inside. Oh no, I have to check speed of the wave. Okay, so see you in the next one.